I want to talk now about the role of engineers in dealing with coronavirus. I'll start by talking about the particular tools that engineering and engineers bring to the problem. Three particular paradigms that have an engineering basis, and finish up by mentioning non-medical or pharmaceutical interventions that are often engineering or require engineering skills in their design, optimization, and implementation. The first tool that engineers bring is an understanding of how much of a material is there, how frequently the material occurs, how far does it go, how is it transported, and finally, what is the uncertainty in measurement of the material. The second broad tool of engineering is our ability to take a complex problem and decompose it into parts and subparts. And each of those subparts or even sub-subparts are amenable to analysis and solution that we understand. Then we can reassemble the parts together and get an overall understanding of the big problem that we're trying to get our hands around. Now, there's a danger in this that we always need to be aware of, and that's emergent properties. We need to be able to do the decomposition such that there's not interaction amongst the various subproblems that we're looking at. A second broad set of tools that engineers bring to the table in understanding the problem at hand is the application of conservation laws. And in this case, we'll focus particularly on mass conservation. We start out by dividing the universe into two, a system versus surroundings. And then we focus on what happens within the system. And often we define our system to make it convenient to do the analysis. So if we look at mass conservation, one way to express a mass balance on our system is that the rate of change of mass or mass of a particular material in our system is equal to the rate of inputs minus the rate of outputs plus or minus any rates of reaction. And you might think of this as a chemical, but in our particular case, the mass that we're looking at could essentially be a virus, where we're looking at the rate of change of living viruses in our system equal to the rate of inputs minus the rate of outputs, plus or minus any rates of reaction. And in this case, the rates of reaction could be inactivation, or if we're in the body of a host, could be the rate of multiplication. As we know from engineering, the way that verbal statement is expressed leads to a natural formulation in terms of differential equations or possibly partial differential equations, which we know how to solve. Don't worry, we won't be doing PDEs in this course, but we will be doing some problems that have ordinary differential equations as their natural means of expression and solution, which we'll accomplish numerically. The three particular paradigms that have engineering bases to them. First are the concept of balances that I just talked about. The second, which environmental engineers are very used to, but it manifests itself in other contexts, is the concept that to look at the effective material on some individual, we have to have a source. That material needs to be transported. And it needs to be transported into a receptor that is then exposed to the material. As you see from the photograph on the left, this is an example of an individual being provoked to emit a sneeze. And there are aerosol particles and droplets going away from the person into the air environment surrounding him. We have a source of microorganisms from that individual. We need to know how they move. If you look at the right-hand figure that expresses in more detail the type of pathways that we may have transport directly via close contact to another individual who's susceptible very close by. In other words, those particles directly impinge on the eyes or nose or mouth of the individual on the right-hand side of that graphic. We have two other routes that are called the airborne route, where those droplets linger into the atmosphere for a period of time and then are eventually inhaled after perhaps having the opportunity to die off, to inactivate by a susceptible individual on the right. And then we have a third route, which is called the fomite. Now, a fomite refers to a non-biological surface onto which microorganisms from droplets or aerosols are deposited. Some of them may persist on that surface. Some may die. They can be resuspended by air currents from that surface, or we could have an individual who inadvertently touches that surface, gets some of the viruses on their hand, and then by hand to mouth or hand to nose or hand to eye touching, there's an opportunity for the virus to go into the body tissues of the susceptible individual on the right. So all of those pathways embody the concept of having a source, the concept of transport, perhaps with some opportunity to decay, to become inactivated, and then some opportunity for the susceptible individual who's the receptor to encounter what may remain of the living viruses and take them into a portal of entry, whether it's the nose or the mouth or the eye, or perhaps in other pathogens that's spread by other routes via broken skin or elsewhere. The third major paradigm, now I should say we'll talk about the details of transport and inactivation and transference as we go out throughout the course. The third major paradigm, particularly that environmental engineers, but also others are used to applying, is the risk assessment paradigm. Now, in risk assessment, First, we identify a hazard. In this case with coronavirus, we know what the hazard is. We estimate the exposure by various routes. We combine the exposure with knowledge of the potency of the organism, which is expressed in terms of the dose-response relationship, which we'll talk about. And then we get an overall risk from the distribution of exposures and the dose response, which we characterize. When we characterize the risk, and this entire process on the left-hand side is called risk assessment, we can now use this as a basis for making a decision or taking action if we examine the possible costs and benefits of the action, for example, vaccines, drugs, or non-pharmaceutical interventions. Looking at economics, looking at social factors, looking at political factors, and any other technical data that may emerge to take action. And then, of course, after the action is taken, in this risk management process on the right-hand side, we can assess how well that action has performed and maybe revise and update what we do. And then finally, many non-pharmaceutical interventions, which we'll talk about, are really dominated by engineering concerns. If we want to control exposure via inhalation indoors, we can look at modifying ventilation in a building or a room by increasing air circulation, by increasing air intake from the outside, perhaps, by changing temperature or humidity. We can look at various filters, both at a room scale and an individual scale, whether we talk about individual masks, filters on the air conditioning, and so forth. And filtration and design of filtration materials and their optimization is really, to a large degree, an engineering concern. And then finally, we can include processes for deliberate inactivation in the indoor environment, in the medical environment, or wherever, whether it's the use of ultraviolet light, chemical disinfectants, heat, or other processes. The role of engineering is to help design and optimize the particular processes that might be employed and to determine whether or not they're fit for achieving the goals that we want to achieve. So I'll stop here, and then the third module for week 1 will be some basic biological concepts that we'll need to understand to deal with the issues of concern. Thank you.